Hi, good afternoon. I am Rulin Van Dyke with Agilent ESOF, working in the system simulation area. Would like to talk about simulation of phased array radars and some of the design challenges that designers face. As you know, the tolerances are becoming tighter, and it's expensive to do field tests, of course. I mean, you just don't go rent an airplane and start doing tests in the air. So what you'd like to do is do some of the simulation, some of the algorithm development, some of the analysis before you get to the field. And even doing field measurements are a challenge. So some of the things that we're going to look at here is the transmit-receive modules and the direct digital synthesizers that are used, and the digital analog converters. And as you think about the trends in phased arrays, they generally have been very passive, and now they're going more to an active approach. And so now we're finding that TR modules associated with each element, and that means digital processing for each element, a DDS as a signal generating source, and then an analog to digital converter on the back end. One of the other challenges that individuals face is there's RF, of course, there's signal processing, and how do we bring these together? And a lot of times the signal processing engineers and the RF engineers sometimes live in two different worlds. Calibration can also be difficult and challenging, especially when we come to a large number of elements. So how do we streamline all this and bring all this together? So on the left, you see generally a traditional approach, which is the passive antennas. And here, most everything in that schematic, in that block diagram, is RF. So you have a transmitter source, you have a high power amplifier, and then you're doing some sort of beamforming, of course, with some digital control. And then the phase shifters, and of course the antennas and all those are at RF. So some of the challenges there are the isolation between the antennas. Now, if we look at the active antenna system, this has got some nice ideas and nice concepts where we can have a TR module that's very localized and that we have for each particular element. But sometimes when the phased arrays have large number of elements, I mean, we're talking thousands of modules that we need to design for. And so what's the best way to balance out, you know, is there a way that we can use the same digital to analog converter for several different TR modules and so forth? Of course, the beamforming here in this case is all done at baseband, and so the output coming out of the TR module, this is the one on the right, the active antenna, is all baseband. So all these things can be done at a baseband level. All right, and so we have a platform that we use to bring all of this together for the active electronic steerable or scanning antennas. So of course, the DUT is important, and test equipment and being able to measure it, but that's kind of expensive to when you get to that part. What you'd like to do is do as much as you can in the simulator ahead of time. And so, of course, you're looking at algorithms for beamforming, also down conversion, and what's the best way to break down the arrays, maybe large phased arrays, into smaller arrays, and then maybe doing some of the digital to analog conversion on smaller arrays or subarrays. Of course, the antenna patterns are important. They have side lobes, and you want to be able to understand the impact that the side lobes have on when you're looking at a target and looking at reflections. What you'd really like to do is be able to prototype some of this. Also, looking at the RF imperfections, right? What happens with intercept point and noise and those sorts of things. And so we have an environment where we can bring all of these together. And so, you know, in the past, users maybe have used in the RF world a scanning oscillator. Well, some of the key models here would be a direct digital synthesizer. And then, of course, with the radar, we want to generate a certain type of pulse. And so with our DDS model here, you can select some of the types of signals and pulses that are commonly generated. Also, another important model is the radar cross-section. And there are lots of different types of radar cross-sections that are by default in this particular model. And so, of course, we can look at the ground effects and the atmospheric losses, of course, the system losses, ground reflection, polarization, and all the other things that are important when you're looking at radar. All right, we also, there's clutter models that we can look at the different characteristics of clutters, and the users can define what those characteristics are. Two other really important models here that seem pretty simple here, but are very complicated and very useful is the whole phased array. So in these particular models, you can actually specify what type of array you have, what the dimensions are of the array. You can even specify the target angle and be able to use these models to simulate the direction of the radar. And then, of course, beam steering. We have examples that show the signal processing and the other beam steering that you want to look at and be able to use in the simulator. So this is just a simple linear array of elements, and we see the signals coming in at a particular look angle. And then, of course, you want to be able to look at what happens at all the different look angles. Where you're getting signals at a side lobe. Maybe in the beamformer you want to be able to steer your beam so that you put a null at a particular location and be able to look at the effects of that. And then, of course, there's lots of measurements that we have in the tool where we can actually look at the antenna patterns. We can look at the different side lobe levels. And, of course, we integrate with MATLAB. So if you have IP, and a lot of customers have IP in this area, we can bring that type of IP into the tool and be able to use it to do the simulation. Okay, one of the other things that's really important is RF co-simulation. So in this particular example, on the spectrum on the left is frequency hopping. So we see a signal at 1.3 gigahertz, 1.5, and I think 1.7. So we want to be able to generate that sequence and be able to analyze or co-simulate with our RF. Well, we have a waveform composer sequencer, which is also used with the instruments, where we can actually take simulated waveforms, we can construct those waveforms, and then we can sequence those out through actual hardware. So you can do it in the software as well as in the hardware. Then we have our little RF block here in the middle, which you see at the top. We support X parameters, so if you have an X parameter file, you can co-simulate with that. Also, there's behavioral models if you want to start it and look at that level. And then also we can co-simulate with AESA. Now on the very right you see a sync, and you won't be able to read those words, but it says VSA. This is the vector signal analyzer software that we sell with both the hardware and also with System View, and you can buy it for the software. So you can use the same simulation analysis software with this phased array simulation as well as with the actual hardware. So you're using the same type of equipment and software to look at different aspects, EVM and various digital demodulation aspects of the signal. All right. We are integrated very tightly with hardware. And so, like I said, we can generate signals, drive it into a signal generator, be able to run those into your device under test, and then be able to analyze those particular waveforms, and then you can compare it to the simulation results. And so all of this helps, when you're trying to look at detection rates and false alarm rates and looking at complex signals, looking at linearity. Maybe you want to do digital predistortion. So here's a little simple example where we're comparing the algorithms for two digital down converters. And this is, so you see at the top the co-simulation with ADS, and then on the far left is there's a little picture there of multiple transceiver modules. And so the little graph at the bottom on the right shows the difference in the error rate comparing the two different digital down converter algorithms. And so this will help you make a better choice before you actually get to the hardware. In this particular example, what we're doing is we're doing active error correction. So there's a reference channel that we have, and then our main channel, and we can develop algorithms to compare the amplitude and the phase error and then do the correction. So you see on the graph on the lower right, the red trace is the original signal without the error correction. And then once the algorithms that we've developed and are put in place and we want to test, once we run those through the systems, then we see the blue trace at the output, see the correction. All right, in this other example, what we have is we actually have two, in this particular case, two 16x1 transmit arrays, and they both have beamformers, and then these beamformers are being combined together, and then we have two receivers. And basically what this shows is that we're able to detect these two signals, and that's what we show here at the graph on the bottom. All right, so the benefits of having a tool like this is you can look at trade-offs in the software and develop all your algorithms. Look for the phase and amplitude errors, and be able to analyze the radar in a near real environment, as real as possible, looking at all the different imperfections and problems that you face. Be able to look at the effects of the antenna pattern and be able to understand the impact that they have on the phased array. And then, of course, all the metrics that are used for phased arrays, the false alarm rate, the detection rate, and the whole purpose is to help you get to market sooner, be able to leverage the IP that you have with MATLAB or whatever else you have. All right, if you have any additional questions, you can come see us over at the Agilent booth. Thank you.